right, welcome back for section 7.2, Exponential Models in our Calc 2 class. So this too should be pretty much a review, not necessarily from Calc 1. We didn't do too much with exponential models, but you certainly did it in pre-calculus classes. So a quick review of the formulas. What we're talking about here is exponential growth and decay. All right. So if you recall, exponential growth and decay, the function for it has to start with some initial value. And that's going to be our y sub 0. And that's the value at time 0. And it gets multiplied by our exponent, the rate constant, times time. So k is our rate constant, and it's pretty much the average growth throughout the time period we're talking about, or decay. And t, of course, is amount of time. Often we'll be given initial value and another value, and we can use that information to get our k to then go on and solve other problems. So basically, when our rate constant is greater than 0, we experience exponential growth. And when our rate constant is less than 0, we experience exponential decay. We can also use this information to determine what we call doubling time, meaning the time it takes to double our initial value. And to double your initial value, we call that t sub 2, time it takes to double. It's actually always equal to ln of 2 divided by your constant. Of course, that means your constant is greater than 0 because we're doubling our value. Now, on the opposite end, if we're dealing with decay, we have something called a half-life. And that is represented by the time it takes to cut our initial value in half. And that is equal to ln of 1/2, and it makes sense, k. And of course, in this case, k is going to be less than 0. In order to, if your k is greater than 0, you can't get the time it takes to get a half-life because you're increasing, you're not decreasing. So these are some basic formulas. There is another one I kind of wanted to put out there before we begin, and it is this idea of energy consumption. So, of course, you can use your exponential growth to talk about the growth of energy consumption or the decay of energy consumption. But one thing I wanted to point out, and this is very similar to what we did in 6.2, suppose we have two functions and we let e sub t represents total energy used. And that could be total energy used by a person, by a city, by a machine, by whatever's given in the problem. Then your p sub t, which is your rate, that could be the rate at which energy is consumed. So these are going to have a very similar relationship to our position function versus velocity, in that p sub t which can be represented with a growth or decay function, of course, is going to be the derivative of e sub t. Or in other words, e sub t from time a to b is the integral of the rate function. So as we go through this, just keep this particular relationship in mind, which is very similar again to, remember the fact that velocity is the derivative of the position function, so therefore your position function is the integral of your velocity function. So just kind of keep those relationships in mind. And again, I think you've seen a lot of this before, so we're just going to go through a couple problems from the textbook. And we'll start with an exponential. In this case, we're going to do growth. Decay would be done exactly the same way, so I'm just going to do one of them. We're going to do an exponential growth problem. In this particular problem, it is number 22 in your textbook in section 7.2 that we are in right now. So if you need to go back and take a look at the problem because you're looking at your notes, you're not sure what you wrote down, just turn to section 7.2 and look at exercise number 22. And it has to do with tortoise growth. It's called tortoise growth. So in this problem, a study conducted at the University of New Mexico, it was found that the mass of juvenile desert tortoises exhibited exponential growth after a diet switch. So at the time a new diet was put in place, so our initial time, our tortoises had a weight of about 64 grams. Then, 33 days later, the tortoise had a weight of 73 grams. It went to 73 grams. The question, first question, how many days to get the tortoise up to 100 grams? All right, well, what we have is an initial value. We have the change. What we don't have is our rate constant k. So we need to get that first. So to set this up initially, we know that we ended up at 73 grams. So that's going to be essentially our answer, right? 73. Our initial value was 64. We don't need K, we don't have K. That's what we're looking for. It took 33 days to get there. That's all you need to do. All right. So we have to do a little algebra work first. Divide by 64. Get that exponent by itself. And then turn it into a logarithmic problem. So it's ln of 73 over 64 equals 33k. So k is going to be equal to the natural log of 73 divided by 64, and then divide by that by 33. Just use your calculator, and you get k equal to, I believe it's 0.009 0.04, but you might watch. I paused for a second just to make sure it is. It's like 0.0039 something, so we're just going to call it 0.004. Once you have the K, now you can go and see, well, what are they asking? Because you can't really do anything until you have that rate constant. Oh, how many days to get to 100 grams? Okay, well, that's my value I want, so that goes out here. Remember, your initial value is still 64 grams. You now know K is 0.004, and we're looking for T. So hopefully, again, these problems kind of ring a bell. So then ln of 100 over 64. I'm going to skip right to dividing by 0.004. It's going to equal my time. And it's a decimal. It's like 111 point something. So we're just going to round it to approximately 112 days. Yeah, they're that easy. I can ask a follow-up question. So remember, we started at 64 grams. We have not yet doubled in weight. So let's figure out, hey, how long will it take to actually double in weight, right? So that's that T2 function, which is simply ln of 2, since we're doubling, divided by our rate constant. And we can calculate that real quick, which I did not do yet. So let's do ln of 2, which is like 0.693 divided by 0.04. It's about 173 days. A little more than 173 days. Now, let's do one of those energy problems that we have. I'm going to go same page, just a couple problems down to number 24, energy consumption. So let's date, we just had a new year, so on the first day of the new year, a city used 2,000 megawatts. Used electricity at a rate of 2,000. The rate is projected to increase of 1.3% per year. So the first thing we're going to determine is the exponential growth function for the power rate, the rate of electricity use for the city. Function. P sub t. Because we want the rate, find the exponential growth function for the power rate of electricity use for the city. So that's our P function. So what do we know? Well, we know we have this initial value of 2,000. E So we can use this projected value to get our K and say that, well, after 1 year, then we would have 2,000 times 1.013 2026. Then we can go ahead and put in 2026 equals 2000 e to the k times time was just 1 year. If you work that out, you will end up with k equaling 1.013, which, yes, is very close to this value right here. It's just a little bit more accurate. So our exponential growth function is going to be our initial value, whoops, I forgot the ln. I went through that way too fast. If you work it all out, you end up with ln of 1.013. Times t. That would be our function. And then we can use that function to determine, right, number 24, I lost my problem, total energy used by the city over 4 full years. We want total energy used over 4 years. Well, total energy is our E sub t function. And E sub t equals the integral from A to B, which of course is 0 to 4 in this case, of my P sub t function, dt. And you can use the integration techniques that we went over, the general techniques. You need your U sub, which is your ln. If you do U sub, you need the derivative of, you let U be this exponent up here, which means you're going to need a 1 over ln 1.03. So you have your 2000 over ln of 1.013 e to the ln 1.103 times t going from 0 to 4. And you just have to plug all that into your calculator, and you plug all that into your calculator, and you should get about 80,210.3. Okay, so practice some of those problems, and again, most of this, except for this idea of getting total energy from the rate, should be all review.